So today it's my pleasure to introduce Hoyos, talking about holographic description of first order phase transitions.
Thank you. Thanks to the organizers for inviting me here and to this nice program. So many interesting talks already. So I'm going to talk about some recent work about these transitions. So let me give you some motivation of why I started looking into that. So first, I got interested in this kind of thing because of these phase transitions in the early universe in cosmology. So the point there is that in the standard model, there are no phase transitions, but if there was a first order phase transition that can produce a gravitational wave signal that you might detect, and then that will be a signal of new physics. Okay, so people, of course, have studied many models of this transition, but typically they are weakly coupled models, but there is no reason why the physics of this possible phase transition should be weakly coupled. Okay, so we started looking into that. And then there is another motivation from much more microscopic physics, from nuclear physics. So this is the phase diagram of QCD, this is temperature, this is baryonic density or baryonic chemical potential. And people believe there is a first order phase transition here, separating confined from deconfined phases. But this is just an educated guess from phenomenological models. So now people is trying to look into these first order phase transitions and this endpoint, critical point, using heavy ion collisions. Okay. And then there are also some interesting physics in neutron stars that happen around this part of the phase diagram. So it's the properties of these neutron stars can depend on whether there is a first order phase transition here or not. Okay. So this, of course, is strongly coupled, and actually there are no other, we don't have any first principle technique to tackle this part of the phase diagram. Okay, we cannot use perturbative techniques because this is not weakly coupled, and we cannot use something like numerical Monte Carlo because there is a sign problem. Okay, so then, yes.
What's the axis on the plot?
Yeah, this is temperature, and this is baryonic chemical potential. Okay. So if you are here at zero chemical potential, then you can use these lattice QCD calculations to find what is the phase diagram. But here there are no phase transitions. Okay, so finally, I think, which is more the topic of this workshop, we know there are these strongly correlated electrons that, of course, they are also very hard to describe from first principles. In this case, one can, let's say, study the phase diagram just experimentally, right? As opposed to these other cases where you can only study it indirectly. And then, well, it is interesting to see what kind of phase transitions you have between the different regions in this phase diagram, whether they are first order, second order. Okay, so you can imagine devising some experiment that explores what happens when you move from one part of the phase diagram to another. Or people also study quenches, where you do a very sudden change in the system and you want to make it evolve from one part of the phase diagram to another part of the phase diagram. Now, in all these cases, in many of these experiments, in these observations, the phase transition doesn't happen in an ideal way where you take infinite time to make the phase transition and you go infinitely slow, so you are always close to equilibrium, right? In these heavy ion collisions in the early universe, in these quenches, for instance, everything happens in some finite time. You have some real-time evolution, and then the system is taken out of equilibrium. You could be closer to equilibrium or farther away from equilibrium, but you're out of equilibrium. No, and if you have temperature, you have other things to take into account, like dissipation, thermal fluctuations that can influence the transition itself. No, and then we know that equilibration rates can be very different between weakly and strongly coupled systems. No? So we have this example of Planck dissipation, as opposed to weakly coupled dissipation. So it is interesting to have some tool to study these strongly coupled systems in this kind of out of equilibrium setup. So for that, I will use these holographic models as some theoretical laboratory to study this kind of evolution through phase transitions. Now, let me just do like a quick review of this phase transition. So this is something everyone knows here, but this is to set up notation, let's say. So something that will be connected to these holographic models is an effective description in like Ginsburg-Landau. So the idea there was you have the order parameter psi that you use to characterize the phase transition. And then there is an effective potential for this order parameter that can have several terms depending on the powers of the order parameter and some coefficients. And the coefficients can depend on temperature, for instance. So the canonical example is where the mass depends on temperature in this way. But in principle, you could have more complicated potentials than this one. And that I would call that mean field, but it's not the classical mean field that people talk about, which is just this model. Now, if you are at very high temperatures, then you have some positive mass here, and then the effective potential will just have one minimum, like this red line. And then as you lower the temperature, then this is going to zero and eventually becoming negative. So what happens is you start developing another minimum here, and this minimum can become more favorable than the original one, and then you will have a first order phase transition. And then eventually this minimum can disappear and you just have this other one. Now, you can use the effective potential to compute the free energy of the equilibrium states. So the idea is that each of the critical points in this effective potential correspond to some equilibrium state, and the free energy is determined by the value of the effective potential at that point. Okay, so if you plot the free energy as a function of this parameter, then this is the, let's say, high temperature minimum that evolves in this way, the value of the effective potential at that point. This is the second minimum that evolves in this way when you change the temperature. And then this purple line is the maximum. Okay. And then you can also picture what is the position of the equilibrium state in the order parameter. So this is the position of the high temperature minimum that is evolving along this line. This is the position of the low temperature minimum that is evolving along this line, and this is the position of the maximum. Okay, so this is a plot for the order parameter, but you can have similar plots if you have here the energy density or the entropy density. They will look kind of similar to this plot. So here you see that the value of the free energy of the two minima coincide at this point. This is where you have the first order phase transition, and that corresponds to this dash line here. So if you start from high temperature and decrease the temperature, when you reach this point, then you can start having a transition from here to here. Okay, so this red line here is stable, this blue line here is stable, and then this red line in this part is metastable, and this blue line is metastable. And here, which is a maximum of the effective potential, is always unstable. So this is the picture of the first order phase transition. Now, in the second order phase transition, you can have a similar thing, but you just collapse this purple line to a point, and then this purple line collapses to a point, so just the blue line and the red line will be joined together. But otherwise, the second order phase transition looks similar. Now, how the transition happens when you are evolving in real time. So typically, if we think about water, for instance, when we heat it up, then we will produce bubbles of vapor inside the water. And this is the picture, the general picture you have for these first order phase transitions. No? So I'm always going to think in this talk about cooling, but you could also think about heating. So we will start here at high temperature and then decrease the temperature. And then when we reach this point, we keep decreasing the temperature, then we can start forming these regions where this stable state is inside this region and the metastable state is outside. Okay, so there is some probability per unit time per unit volume. This is the nucleation rate of producing these bubbles. And then the probability depends on the cost in free energy of producing the bubble. So there is a critical size for this bubble where the bubble, if it's smaller, will just collapse back to the metastable phase, or if it's larger than that, it will expand. And then expanding these bubbles will collide and eventually will eat up all the metastable vacuum and leave only the stable vacuum. So how this happens depends on crucially one quantity, which is the velocity of expansion of this wall. Okay, so to characterize the transition, these are like the two most important quantities, the nucleation rate and the bubble wall velocity. If this is very small, then it could happen that you don't nucleate enough bubbles to complete the first order phase transition before you reach this point. Okay, so we'll call this point a spinoidal point. This is usually called the spinoidal branch, the unstable branch. So this could happen that you reach this point if fluctuations are suppressed. So this nucleation rate is suppressed. So what happens in that case? Well, so assuming you always have a homogeneous state and then this bubble nucleation or other fluctuations are suppressed, then we know that in second order phase transitions, there is no bubble nucleation. So what happens there is you see this phenomenon of slowing down. So you can have some perturbation that takes you a bit out of equilibrium. And typically this thermalizes and dissipates, right, in a normal situation. But as you come closer to the critical point, the time it takes for it to dissipate becomes larger and larger. So eventually it doesn't dissipate at some point because it takes longer and longer times. Okay, and then you also see some kind of scaling behavior of how you are taking out of equilibrium. Okay, so there is some scaling law that is determined by the critical points of the, for the critical exponents of the critical point at the second order phase transition. Okay, so what happened here then in this second order phase transition is that there is some relaxation rate that is going, relaxation time that is going to infinity, and there is also some correlation length that is going to infinity. So this is well known for second order phase transitions. But for first order phase transitions, if you are reaching the spinoidal point, the situation is actually quite similar. Okay, so you see similar critical slowing down and scaling behavior close to these spinoidal points. Okay, now the spinoidal points they don't have to fall in the same classification critical points as the second order phase transitions. Okay, so you could have a different set of critical exponents in these spinoidal points. Now, there are actually some observation of this situation where all these fluctuations are suppressed and you reach the spinoidal point. So, well, this is one case I know, but there are more. So here you have this transition between an insulator and a metal in this material. And then the experiment consists on lowering the temperature or increasing the temperature slowly. Okay. And then what you see here in this part of the evolution is you are in the stable or metastable branch, and then you reach the spinoidal point, and then you fall down. So this is a completely out of equilibrium evolution, and then you go back to the stable branch. So between this, so this is the opposite evolution, which you are cooling down. So the spinoidal branch will be joining these two knees here in this evolution. The spinoidal branch will be somewhere in between these 2 points. So these people study this evolution of the system through the phase transition, and then they find that the temperature where you go out of equilibrium has some scaling behavior with the rate with which you are changing the temperature. Okay, so this are essentially Kelvin per minute. This is the velocity with which you change the temperature, and it follows some scalings.
First question.
Yeah.
So the claim is that this is a homogeneous first order phase transition with no nucleation?
Yes.
Didn't know that could exist.
Yeah. So you need to suppress the fluctuations in some way.
Okay.
Yeah.
What would be suppressing these fluctuations?
Yeah, in this system, I don't know what is exactly suppressing the fluctuations because I'm not an expert in this. In the case of holographic models, it's something you might expect because going back to this nucleation rate, this free energy is proportional to the number of degrees of freedom of the system. And as I will explain in a minute, the number of degrees of freedom in this holographic system has to be taken to be very large. Okay, so there is a natural suppression in these holographic systems of the nucleation rate. So it's perfectly possible that you reach the spinodal point before you are able to complete this process.
So maybe they just cool faster than the system can.
Yeah, exactly.
But yeah, the issue with first order transitions is always getting the heat out, right? There's latent heat. So you have to remove this thermal conductivity that's involved.
Yeah, so here I'm talking about an evolution where you are connected to a thermal bath. So yeah, in this experiment, you change the temperature, which means you have a thermal bath where you control the temperature and you put the system in contact with the thermal bath.
Okay.
But if you do the evolution in a different way, like not by connecting to a thermal bath, then things can be different. I will talk a little bit about that. Okay, so this is the introduction. So let me explain a little bit about holographic models. I think this is the first talk. There will be a review talk next week, where you will understand better what I'm going to explain here, but, just to give you a flavor of what we do. So the idea is the following. So we have some quantum field theory, which in the case of applications to condensed matter, it will be like the strongly correlated electrons. And they live in some number of dimensions that are parameterized by these coordinates x. No? So typically they will live in 2 space dimensions or 3 space dimensions. Now, this is a strongly coupled or strongly correlated system that we don't know how to describe really. So the idea of holography is that you can map this to some other theory, which is a theory that contains gravity. It lives in one additional dimension. So this is the additional dimension set, which is called the holographic radial direction. And this direction encodes information about the renormalization group flow. So essentially, there is some asymptotic boundary. When you are close to the asymptotic boundary, you are at very short length scales or very high energy scales. And when you go away from the boundaries, you go to lower energy scales or longer length scales. Okay, so in principle, you have here a full theory of quantum gravity or a string theory, but you can do some simplifications. So if in this theory that lives in the real world, you have a lot of degrees of freedom, this is called the Largen limit. But you are also familiar, no? If you think about sigma models, for instance, you can take a Largen limit. Then you can ignore quantum corrections in the gravity side, and then everything is described by a classical theory. And then if in this theory that lives in our world, you are strongly coupled or strongly correlated, then that corresponds to suppressing higher derivative terms in the gravity part. Okay, so in principle, Einstein gravity itself, from the point of view of quantum gravity, is an effective theory. It will have higher derivative corrections, but they are suppressed if you are at a strong coupling here. Okay, so this is actually very good because when the system is more complicated on the field theory side, it's simpler in the gravity side. Okay, so that is helping us out. But the price we have to pay is these larger limits. No? So this actually is what is making this a bit like a mean field theory, taking this semi-classical. Now, this is some geometry, and you can have also black hole geometries. So this is what is represented by this black square here. There is a black hole and there is a horizon here. So this is not a spherical horizon like in Schwarzschild, but it's a horizon which is parallel to this asymptotic boundary. So it has infinite extension. And then the properties of the thermal properties of this field theory are encoded in something that are black hole thermodynamics. Okay, so the temperature is the Hawking temperature, for instance. Okay, so the upshot is that I can encode all kind of thermodynamic and dynamic properties of this correlated system inside this classical gravity that lives in one more dimension. Now, this is how the map will work. So suppose I have a strongly coupled field theory in 3+1 dimensions, then I have classical gravity in 4+1. We're interested in the phase transition, so I should have some order parameter that will depend on the coordinates in general. And then that maps to some scalar field, classical scalar field in the gravity side. And then the energy momentum tensor is mapping to the metric. And then a thermal state where all degrees of freedom are excited, which is this n squared, then that corresponds to the black brane geometry I was describing. So for instance, you can compute thermal properties by looking at these thermodynamic properties of the black hole. And then you can compute correlation functions in this strongly coupled theory by looking at classical fluctuations of this scalar and the metric on this side. Okay, so that give us the map between the two sides. Now, something that is important here is that I can choose the sector that is going through the phase transition to have a number of degrees of freedom, which is much smaller than the total number of degrees of freedom. Okay, so that means the geometry is acting as a thermal bath, and then the phase transition is happening inside this thermal bath. Okay, and then that means that the metric will be always the same, but I will change the value of the scalar field without backreacting on the metric. Now, a second possibility is that the whole system is undergoing the phase transition. Okay, and then I have a fully backreacted geometry where the scalar field is changing also the metric. Okay. To do this, we will take some particular models that were introduced by these people that have these phase transitions. Okay, so essentially you choose some action for the scalar field, and then you find solutions, and then you can find several phases depending on whether you have several solutions or not. Yes?
So you said the black hole is not like curved, it's just a flat sheet, is that?
Yes, so this geometry has an asymptotically flat boundary, okay. And then the black hole is parallel to this boundary. The horizon is parallel to this boundary.
And do you have to show that that's a stable solution to the Einstein field equation?
Yeah, but in this, in all these setups is stable. Okay, so let me. So if you have a phase that is stable or metastable, then the black hole is stable. And if you have an unstable phase, like this spinoidal phase, then the black hole is unstable. And then you can study the stability by looking at these fluctuations.
Thanks.
Thanks for the question. Okay, so let's go and study the dynamic and thermodynamic stability. Okay, so first let's think about the weak coupling version of this. So I'm going to think about the scalar order parameter is coupled to some thermal bath of fermions. Okay, so there will be some interaction that could look like this with some couplings lambda and some number of fermions that are coupled to the order parameter. Okay, so in high energy physics, this order parameter could be the Higgs field, and this could be the fermions, or you can also add couplings to vector bosons in the standard model. Now, you integrate out these fermions that they are just in a thermal state, and that produces some correction to the potential of the order parameter. So here, this will be like the 3-level potential that produces a spontaneous symmetry breaking. But then you have additional corrections that come from integrating all these fermions in the thermal state. So first, there is this part which is just like a free massless fermions, right, contribution. And then there is this contribution that comes because of you have this coupling, so the fermions acquire a mass that depends on the order parameter itself. No? Now, this part, if this number of degrees of freedom is large enough for the thermal bath, this part is dominant. And what happens is that gives you a positive specific heat always, independently on which phase you are in. And that means that all phases are thermodynamically stable. Okay? That means also the spinoidal phase is thermodynamically stable. Now, there will be a dynamical instability in the spinoidal branch. So you can compute the correlation function of the order parameter at 0 momentum. And then you should see that there is a mode that in principle behaves exponentially with time. So if you do the Fourier transform, there is a imaginary Pauling frequency. And this gamma, this width, depends on the second derivative of the effective potential. Okay? So if you are at a minimum, the second derivative is positive, and that means this exponentially decaying. So that's the stable or metastable phase. But if you are at a maximum, like in the spinoidal, this second derivative is negative, and then there is a dynamical instability. Okay? So this is the mode that determines this behavior. Okay, and notice that when you are approaching the spinoidal point, that's when a minimum and a maximum are colliding, and this second derivative is going to 0. So that's what is giving you the critical slowing down. There is a relaxation time that is going to infinity in that case. So that's the picture. Now we can do a holographic calculation and compute the phase diagram and the correlation functions and look at these poles in the correlation functions. So here I'm plotting what happens when you are at weak coupling. Or you are in this probe approximation where the scalar field doesn't back react over the geometry. Okay, so you always have a thermal bath that doesn't care about what the order parameter is doing. So we have the entropy density in some units and the temperature here. And then you see that these two branches will be the stable or metastable branches, and the one in the middle is the unstable branch, the spinoidal branch. But you see that the slope of the entropy with temperature is always positive. So this is thermodynamically stable in the 3 phases. You look what happens at fluctuations, then I'm plotting here like what happens in the scalar channel. And so this is the imaginary part of the frequency as a function of spatial momentum. This red line that goes to 0 is the sound mode, which behaves like ordinary sound mode. And then there is this dynamical instability I was describing before. No? So it has positive imaginary part at 0 momentum, and then it has some dispersion relation. So eventually at high momentum it becomes stable again. So this is the picture in this situation. Now, if you take the holographic model with full back reaction, then what happens is quite different. So if you look at the entropy density versus temperature, what you see is the stable and metastable branches have a positive slope with entropy, so that means they are thermodynamically stable. But the spinoidal branch has negative slope, so it's unstable thermodynamically. Okay. And then when you look at the fluctuations, you see also a very different situation. So here, this mode that was unstable here is now stable. It has always negative imaginary frequency, but the sound mode itself becomes unstable. So this is the sound mode now, but it will have something like an imaginary speed of sound because the negative specific field. And then it's unstable in this region of momenta. And then again, at high enough momentum, it becomes stable again. Okay. So it looks quite different. Now, in the holographic model, you can actually interpolate between the two behaviors by changing how much back reaction do you have on the metric from the scalar. So if you have full back reaction, you have this situation with thermodynamically unstable spinoidal branch. But if you lower the back reaction, then you can have that the spinoidal branch is thermodynamically unstable in some region, but stable in some other region. Okay. And in fact, this parameter here is tuning the back reaction, and then you can go all the way from this situation to a situation like this, where this branch is stable. Okay, so the type of thermodynamic and dynamic instabilities you have in the spinoidal branch is linked to the number of degrees of freedom that is going through the phase transition, or if you want, to the back reaction on the thermal bath. So this is what the holographic model is telling us. Now, what happens if fluctuations are suppressed? So there are two possible situations. So if you have full back reaction, then temperature itself is not well defined if you are evolving in time, because temperature is really something that you define at thermal equilibrium. So if you are completely out of equilibrium, you don't have a good definition of it. But you can use energy density to characterize the evolution. So you can think of the system as you change the volume, that decreases the energy density, and then you can go through the phase transition doing that. So this is what these people studied in these kind of holographic models. And then if you do it slowly enough, you can reach the spinoidal point and then go into the spinoidal branch. So that will mean the temperature is increasing if you were looking at the temperature, okay? But the energy density is decreasing. And what happens is you have this unstable sound mode, and that will start producing a lot of sound waves around that will completely make the state inhomogeneous, and eventually, depending on where you stop, you can have a phase-separated state in the end of this evolution. Okay, so this is some kind of spinoidal instability when you enter the spinoidal branch. Now, the other case where you have this well-defined thermal bath, and then you can change the temperature in time. So this situation is similar to the one I showed you in this experiment. Okay, so what happens is you have a quasi-static evolution until you reach the spinoidal point. Then you have this critical slowing down, so that always takes you out of equilibrium. The quasi-static evolution will break down, and then you have scaling behavior. Eventually, you go completely out of equilibrium and have this kind of change that you jump into the other phase. Now, we studied this in this work, and then we found this scaling behavior. So you can characterize how this scaling behavior is just by looking at the critical exponents at the spinoidal point. Okay, so now I have some questions I want to answer. So first, I use this holographic model to describe all these changes in stability and so on. So the question is, can I have an effective theory description that describes this kind of change in stability when I go from weakly coupled to strongly coupled? And then if there is this effective description, I want to be able to describe it from the macroscopic theory. So we have this holographic model describes the full system. So in principle, I should be able to extract the effective theory from the holographic model. And then if I'm able to do that, how accurate is this effective description? So I can compare the full calculation from the holographic model with the full dynamics with the results from the effective theory. And that will tell me how good is the effective description or the regime of validity. Now, let's first look at the effective theory about the stability change. So the idea is to start from something which is called hydrostatic effective action. So you can describe ideal fluid dynamics from an action just by defining some variables that correspond to the temperature and the velocity of the fluid. So you introduce this vector u mu, and then the temperature is related to the modulus and the velocity to the direction. And you couple it to some background metric. And then you can construct, this is a scalar, you can construct this action with this function P of t. And this action is actually like the pressure of the fluid. So you take the variation of this action with respect to the metric, you get the energy momentum tensor, and that looks like the energy momentum tensor of an ideal fluid. So this should be capital T. Okay. And then from demanding that this is invariant under diffeomorphism of the background metric, you get a word identity for this energy momentum tensor that is just the conservation case. Okay, so you can derive ideal hydrodynamics from this action. Now, now the idea is we can generalize this action and introduce an order parameter, which is this scalar field, and couple it to the fluid. So we can have some effective potential that depends both on temperature and the order parameter. If there was no order parameter, this will be just the pressure. And then we can also have some kinetic terms. So to second order in derivatives, we can couple, this is like the time derivative, and this is like the space derivatives relative to the fluid motion, with some coefficients that depend on temperature and the order parameter. So from this effective action, we can derive equations of motion for the scalar, and we can derive the energy momentum tensor by taking the variation with respect to a background metric. Okay, so this is the ideal fluid that we had before. These are terms that come in from the kinetic terms that I'm not writing them because they are kind of higher derivatives, so they won't be relevant. And this is the term coming from the effective potential. And then I'm adding these red terms here. Now, so the point here is that this is not able to capture dissipation, okay, the way I wrote this effective action. So what I'm doing is I'm adding by hand some dissipative terms to the equation of motion of the scalar and to the energy momentum tensor. Okay, so I could improve this action maybe using a Samsunger-Keldy's formulas to account for dissipation and so on, but I just choose to add the dissipative terms by hand. Now, we can constrain the dissipative terms by using the entropy current. So if you compute the divergence of the entropy current, it takes this form to first ordering derivatives. So it depends on these dissipative terms I added in the scalar equation and the energy momentum tensor. And then if you demand that this remains semi-positive definite, that will be like the local version of the second law of thermodynamics, then this chi is constrained to be proportional to this derivative of the scalar. And then these terms are constrained to have the usual shear and bulk viscosity terms. Okay, and then these coefficients must be positive, all of them. Okay, so actually, this kind of dissipative term was proposed from a completely different point of view in some previous works that were interested in phase transitions in cosmology. And this was derived from considering the interaction of the bubble wall with the particles in the medium. So that will produce some friction. And that will give you this coefficient gamma computed from kinetic theory. Okay. So we recover it here from a more effective theory point of view. Now, we can use this effective theory to compute the specific heat. Okay. So we take the derivative of the entropy with respect to temperature, and we do it on equilibrium states. So if we didn't have the order parameter, this will be this specific heat, like the second derivative of the pressure. So this we can assume is positive. And then when we have this order parameter, we have this extra piece here. Okay. So this is the thing that is actually acting on the thermodynamic stability. Okay. So for instance, if you have a stable situation where you are at a minimum of the effective potential, then this term is positive. So you just have the sum of two positive terms and the specific heat is positive. So that means in the stable or metastable phases, you are thermodynamically and dynamically stable. If this second derivative is negative, that means you are at a maximum. So you are at the sphenoidal branch. Then this term becomes negative. Okay, so now it depends on whether this term is larger or smaller than the first one. Right? So if this second derivative is small, then because it's in the denominator, this term is large, and then it can dominate over that, and that will flip the sign of the specific heat. So that will make the system thermodynamically unstable. But if the second derivative is large enough, then this term is negative, but is smaller than the first one. So again, the specific heat becomes positive, and the system is thermodynamically stable. Okay, so the probe approximation or the weak coupling approximation will be to neglect completely this term, and you will always be in the situation where the specific heat is positive. Okay? But in general, if you have some kind of back reaction, close to the spinoidal points, the second derivative is going to 0. So close to the spinoidal points, you always have that the systems will be unstable thermodynamically. Okay, now one can also take the effective theory and study fluctuations. So you just consider fluctuations of temperature, the order parameter, and the fluid velocity. The equations are simple to solve. It's just some linear equations. And then you find two kind of modes. So one mode is the sound mode that has the usual sound velocity, the entropy density over a specific heat. And then there is a second class of modes that are non-hydrodynamic, that have this dispersion relation at 0 momentum. Okay. And then there is an interesting thing going on with this mode wave and the sound mode. So it depends on how this square root is behaving. So if we have this product of the second derivative of the potential and the specific heat is positive, okay, then this means that this square root is either real, and then these modes are stable because have negative imaginary part, or if this square root is imaginary, the imaginary part is in absolute value smaller than this term. Okay, so in this case, these modes are always stable. Now, if the product is negative, then the imaginary part of this square root is going to be larger in magnitude than this term. So one of the modes becomes unstable and the other stays stable. Okay, and then for the sound mode, it depends on the sign of the specific heat. No? If the specific heat is positive, the sound mode is stable. If the specific heat is negative, this becomes imaginary and one mode becomes unstable. No? So then you see how the thermodynamic stability is related to the dynamic stability. So if you have both the second derivative of effect of the potential and the specific heat is positive, then this is real, and these two modes are stable. So everything is stable. If the second derivative is negative and the specific heat is negative, this product is positive. So these two modes are still stable, but the sound mode is unstable. And here, when they have opposite sign, because the specific heat is positive, the sound mode is stable, but this one of these modes becomes unstable. So this is linking thermodynamic and dynamic stabilities through the indefective theory. Okay, so any questions up to this point?
Yeah. What exactly happens for your dynamics when this sound mode becomes imaginary? Like, how can we interpret what's happening specifically?
So the specific heat is negative. That means it's thermodynamically unstable. So it means if you increase the temperature, the entropy is decreasing. Yes, is something. And then this is a mode that is unstable at non-zero momentum. So what happens if there is some kind of fluctuation that is not homogeneous? That kind of fluctuation will be increasing amplitude, or will start producing sound waves that are increasing in amplitude in some range of momenta. So that will be like this picture I showed you before, holographic calculation. So if you are in some regime where your energy density is between the two stable phases, the endpoint of that evolution typically is a phase-separated situation, where you have one of the stable phases in some region and the other of the stable phases in the other region, so that the total energy corresponds to the average energy, but is distributed in a non-homogeneous way. Yes.
Point. Your second derivative is with respect to phi in the omega equation at the top and then psi at the bottom and top. Is that just a typo?
Yes, sorry. Yeah, this will be psi.
Okay, perfect. Thanks.
So, yeah. Okay. Okay, so now let me talk about the calculation of these bubbles and the bubble nucleation and so on. So we can use the holographic model to find the effective theory. So we did this by looking at the free energy as a function of the external source. And then you can find what is the expectation value of some operator, that's the order parameter. So if you plot it as the order parameter as a function of the source, then you can have this kind of curve. And then if you invert it, you get the source as a function of the order parameter. And then you can use that to reconstruct the effective potential, because it's some kind of Legendre transform of the free energy. No? So if you do it in this way, you find that you have the equilibrium points at the critical points of the effective potential in the right positions and the value of the free energy determined by the effective potential. And then you can use the correlator, the two-point function, to extract the kinetic time, essentially, for the spatial part. Now, there are some caveats here that I'm not going to enter because there is no time. But essentially, the take-home message here is that we can derive the effective action from the holographic dual.
Sorry, maybe if you said it already, but it's important to take omega to 0 first.
Yes.
In this calculation, or
yes. Yeah, this is like a susceptibility.
Yeah, but
yeah, I mean, in general, for non-zero omega, there are dissipative contributions to these correlators that will not be captured by this effective action I was writing.
yeah. So sometimes there's an order of limit?
Yeah.
Worry? Is that?
Yes. Yes, so here you should take zero frequency first. And then you expand in low momentum. Okay. Now, to construct the bubble solutions, so this is merit of my collaborators mainly. So you can just take this kind of geometry I told you about, and then you modify it by introducing some deformation that makes it inhomogeneous. In this case, spherically symmetric in the boundary. That makes the horizon inhomogeneous also, but the temperature remains constant everywhere, okay, despite being inhomogeneous. Okay, so this will be a picture of a bubble in the boundary or in the dual field theory, and this will be the full geometry. So we did this calculation, computed these bubbles, and then we compare with effective theory, this derived from holography, and see that they match quite well. Okay, there is no exact matching. There are some errors, but they match pretty well. I told you also about the bubble wall velocity. This has to be computed by doing some dynamical time evolution of these bubbles that we didn't do, but people did in some other models, and they found that the bubble wall velocity is typically smaller than the speed of sound. So this is what is called the fluorescence. Okay, so let me just conclude. As I explained, there are some qualitative differences on how these phase transitions work in weakly coupled and strongly coupled systems. We can capture this behavior using this effective theory of the fluid coupled to scalar. And we can have a complete microscopic description in these holographic models, with these approximations of large N and so on. And then I told you that the effective action is a good approximation. So in principle, you could even write down an effective quartic potential with some kinetic terms that depends on the temperature. And that will work well to describe these bubbles. But you have to be careful because there is some kind of suppression, like this kind of factor in the kinetic time relative to the naive dimensional analysis. Okay, so actually the strongly coupled theory is telling you that if you just use naive dimensional analysis in your effective theory, you might be going wrong quantitatively, in a quantitative way. Okay, well, you can do also bubbles without back reaction in a probe scatter. This is what people did, and they find a good match also with effective action. And then for the future, well, we would like to improve this construction of the effective action in the dual. I told you there are some problems there. Also, we will like to compute this bubble wall velocity from the effective field theory. So this transport coefficient gamma that appear in the scalar equation that can be used to compute the bubble wall velocity. And then, of course, there is the question of what kind of observable signatures can one find in experiments from either having bubble nucleation or having this kind of two different evolutions. No, either you have this kind of sound wave instability, or you can have this kind of completely breakdown of the quasi-static evolution and then scaling and this kind of things. So, thanks a lot.
We probably have time for a few questions.
You show the non-hydro mode effective action. Do you have some argument about its origin in the holographic model?
Yeah, so this is what we are studying now. So with these people here. So this is still work in progress because we are trying to construct this in the holographic model.
Mm-hmm.
So you just look at the correlation functions of the scalar, and then of the scalar coupled to the metric. So that will capture the sound mode, will be one of the modes that you will see in this correlation function. So essentially, this is quasi-normal modes that you are computing. And then there is a second quasi-normal mode that is not the sound mode, which so what the effective theory is telling you, it will have this dispersion relation. Okay. Now, you can identify this mode because when you go to the spinoidal branch, so when you reach the spinoidal point, this second derivative is going to 0. And then you see that this term can cancel the first term. So there is a mode at 0 frequency at the spinoidal point. So then you can identify this mode by looking at the mode that at the spinoidal point is reaching 0 frequency. And then when you are in the spinoidal branch, this is the dominant mode in the sense that it's the one that is closer to the 0 imaginary part of the frequency. So that means that the effective theory will work well when you are in the spinoidal branch and maybe close to the spinoidal points when you are away from the spinoidal branch. For the bubble nucleation, that's actually what is relevant because the profile of the bubble is mostly going through this field. So asymptotically, you have the stable or metastable state, but essentially it looks homogeneous almost everywhere, and then it starts changing when you reach the bubble wall, and then it has to go through the spinoidal branch to reach the other state. Okay, so the idea is that these modes will capture the dynamics of the bubble wall. Okay, so in particular, not only couple the profile of a static bubble, but this coefficient, the idea is that will capture the bubble wall friction, and it will be able to determine the bubble wall velocity. So that will be the idea. No, so what we want to do is to compute all these parameters that appear in these dispersion relations from either thermodynamics or by looking at the dispersion relation of the quasi-normal mode. And then we can have a general formula for the dispersion relation and compare that to the holographic model.
But gamma should be extracted from the holographic model.
Yeah, so
like
we want to extract
the
it.
formula. It's like a transport.
Yeah, we want to compute this dispersion relation holographically and extract gamma from this calculation.
Yeah, I mean, from the effective field theory, this is just a parameter.
Yeah. I don't know if there is some fluid gravity approach that you could use to extract gamma as well. We haven't looked into that. The idea is to extract it from this quasi-normal mode calculation. Yeah.
Why did you say it's non-hydrodynamic? Didn't you derive it using hydrodynamic?
Well, I use a fluid hydrodynamic coupled to this scalar field.
Yeah.
And then this is a mode that has non-zero frequency at zero momentum. So I call it non-hydrodynamic because it doesn't behave like, for instance, the sound or the diffusion that have zero frequency at zero momentum.
Right. So it's kind of, it would be strange to sound, but it is a mode that appears in hydrodynamics, isn't it? Like it's dissipative.
It depends how you call hydrodynamics, what you call hydrodynamics. So for this to be a good description, so keeping these two modes, in order to keep these two modes and just these two modes, you need that other dissipative modes are have a width which is much larger than this guy, right? So you need like a separation in the imaginary part of the frequency between this mode and the next dissipative mode. So for the sound mode and the diffusion mode and so on, you can always do that by going to low enough momentum. You can always have a separation, but not for this mode. No? For this mode, you have to look at actually what happens with the rest.
Okay.
So when you are at the spinoidal point, one of the modes got zero frequency, so there is clearly a separation close to the spinoidal points.
Yeah.
And then when you go away from the spinoidal points, the thing becomes more, well, you have to look at the model to see if there is really a separation or not.
Can I ask some dumb experimental questions?
Yeah, I won't know the answer.
Does one of these modes correspond to the phase transition front? And that's a sound mode, I guess.
Yeah, this is
So-
sound mode.
Is there a crystallization front somewhere? Because you're at the critical point, right? So there should be something related to the phase transition in the dynamic somewhere.
Yeah, so if you are close to the critical point, that happens when this is small, but you could be away from the.
Yeah,
From
and
the
there's
spinoidal
you said
point
there's
of the
another
critical
mode that's a diffusive mode. Or is this the mode that becomes diffusive when that vanishes?
Yeah, when this vanishes, this becomes diffusive because there is you pick the right hand here, one of the modes has zero frequency at zero momentum.
So the way I understand a critical point is there are fluctuations.
Yeah.
So there's an ordered state and a disordered state,
Mhm.
and there's fluctuations of both of these things.
Yeah.
So that's what this mode is, essentially the propagation of these fluctuations.
Well, here there is no, I don't know if I can talk about order or disorder because there is no,
But there's a phase transition.
there is a phase transition,
First
but
order transition.
it's like a liquid gas transition.
Yeah, so liquid is an ordered state, gas a disordered state. There's a difference in the density. There's a discrete change in the density. So does this correspond to fluctuations in the density between these two states?
Yeah, it's fluctuations in, so this is the order parameter. So there are fluctuations in the order parameter, but they are coupled also to fluctuations of the temperature and the fluid
Sure.
velocity.
The order parameter is basically density, right?
Well, in
Liquid,
this
solid.
case, is like a condensate of sound.
Yeah, so it's kind of a solid liquid and then, or liquid gas, sorry.
Yeah, so this will correspond to these fluctuations of the order parameter. Mhm. And then they will become, no, there will be a critical slowing, I guess.
Okay, so that's front propagation. Is the-
Isn't the unstable mode of this the bubble wall mode?
The bubble wall mode. You mean
Unstable one.
Is there an unstable mode?
compared to the critical bubble? Or,
Yeah, I mean, I think what Peter is asking, right? This is clearly a variation, local variation in the density order parameter. If you're in a regime where everything is dissipative, you just go back to the original state.
Yeah.
When you have a local nucleation of a bubble that grows, right? You precisely don't go back to the initial state. On the one side, you have the ordered phase, on the other side, you have disordered phase. Usually, this is a growing mode.
yeah, so this is not
Growing
corresponding
propagating
to
mode.
the formation of a bubble. So if this if the sound mode is stable and this mode is unstable, then you can have an evolution which is homogeneous and an unstable evolution which is homogeneous. That's like this experiment I saw.
Yeah, I think the bubble wall velocity, I don't think it's captured in this linear regime. I think you need some nonlinear calculation
Yeah,
describing the shape of the interface between.
yeah, I think to compute the bubble wall velocity, you will need to use these equations and the hydrodynamic equations combined. And then you will have the profile of psi to be a bubble profile. And
But
then,
if the height of psi is very small, I should still be able to describe the bubble wall in the linearized regime.
yeah, so if you are close to the spinoidal point, then this will be close to being a linearized fluctuation. Yes. And then you might be able to describe the,
That means there's an overlap between this linearized mode and the generic bubble front mode.
yeah, possibly, but there is no, maybe let me show you.
I mean, the mode has a velocity.
Yeah, let me show you
What's the
some
velocity for, it has to be something physical, right?
Okay, so this is how the bubbles look. So this corresponds to different points on the metastable branch, and this is closer to the critical temperature of the first order phase transition, and this is closer to the spinoidal point. So if you have a bubble close to the critical temperature, it looks like this. So it's large and the wall is thin, so there is a well-defined notion of wall here. But if you are close to the spinoidal point, that is the situation where this mode we are talking about is almost like a diffusive mode, then the bubble is completely like you don't really see a bubble here, you just see like a local change in density, but there is no well-defined wall here.
How are you calculating it?
This is calculated by doing a calculation in the classical gravity theory. So we just impose that asymptotically you have the metastable case, and then you look for an inhomogeneous solution that is spherically symmetric and is regular in the interior. Okay. And then the system finds this solution.
So at the critical, go ahead.
Oh, the bubble in general is found using an instanton solution, isn't it? So then it would be nonlinear. So I guess linearizing would miss it. But like you want to tunnel from one vacuum to another quantum mechanically, or you
Yeah,
can
so
do it
this
classically
is
as well.
this is a fully nonlinear solution,
Yeah, okay.
but here the amplitude is very small. So
Yeah,
it can
exactly.
probably be approximated by a linear solution.
So I think you get it from, yeah, it's like a solution to the classical equations of motion, which are then nonlinear. So you call it an instanton usually.
Yeah.
So I guess it's probably that calculation.
Right. So if you want to look at the profiles,
It wouldn't be described by a velocity, I guess, because that's coming from the linearized case. Like, how do you say?
yeah, so this will be the profiles as a function of the radius. This is like the energy density. So this is close to the critical temperature, the ones on the right, and this is close to the spinoidal point. No? So this is very small amplitude.
Yeah.
Maybe we can finish the discussion during the break, but yeah, why don't we thank Carlos again?
Yeah, so it's the break. So could I just see the dispersion?